Alright, so let's do this example. We're going to sketch the graph of f of x equals x squared minus 2x plus 4 over x minus 2. Alright, so if the degree of the numerator is 1 greater than the degree of the denominator, the equation has a slant asymptote. So on the last problem, we would not even check for a slant asymptote. It had a horizontal asymptote. Notice if we did our limit as x approaches infinity here, this one's bigger on the top, so there's not a horizontal asymptote. Your limit would go to infinity, so this does not have a horizontal asymptote. But because your degree of your numerator is 1 higher than the degree of your denominator, this one has a slant asymptote. If you had something like x to the third over x minus 2, then you wouldn't need to check. It's only whenever it's exactly 1 higher. So if you are in a situation where you have a slant asymptote, which we have here, what you want to do is you have to do, now Coach Wood did teach you how to do this, but you may have forgotten it. You have to do long division of polynomials. And he taught you this before you learned synthetic division, mostly so you would appreciate synthetic division. So that would be like when we did problems like this, x squared minus 2x plus 4, and then you had this x minus 2 out here. So you probably did this, you probably blocked it out of your mind as soon as he taught you how to do synthetic division, because it's a lot quicker. But unless he did something strange, he taught you this first, because he usually does. So it's like regular long division. You have to ask yourself, what times x would give me x squared? So x times x would give me x squared. So you'll divide here. That's what you're doing when you ask that. Then you've got to multiply. So x times x is x squared, and x times negative 2 is negative 2x. So you divide, you multiply, you subtract this stuff, and then you're going to bring down. So we're going to subtract. I always sort of have trouble subtracting here, because when you subtract, you're subtracting this, but you're going to add this, right, because you change the sign. So this will cancel. This one's also going to cancel here. And then you would bring down that 4. Now when you ask yourself what times x would give me 4, you don't have an answer to that, right, unless you try to do something like with an x to negative 1, which you don't want to do. So what you have here, this is just your remainder. So you're going to put plus 4 over x minus 2. Alright. So, in order for there to be a slant asymptote, you have to have a remainder. Okay? If you divide and there is no remainder, then you don't have a slant asymptote. You've got a hole in the graph somewhere. Because if you don't have a remainder, that means if you factored the top, something would cancel there. So if no remainder, there's a hole and no slant asymptote. Okay. But in this case, we have a remainder. So since we do, our slant asymptote is going to be at y equals x. So we leave off the remainder. We just use that y equals x comes from this part right here. So if that was a 2x, we'd have y equals 2x. If that was a 3x minus 4, we'd have y equals 3x minus 4.
Oh, is that the one where it's like right in the middle?
Yes.
Okay.
Yes. The remainder just has to be there. We're not going to include that because that makes that no longer would it be a line if you had that 4 over x minus 2. So that remainder just tells us that, yes, there is a slant asymptote, but we don't include it in our line. Okay, so we have a slant asymptote at y equals x. We still need to check for all of those other things. If you have a slant asymptote, you do not have a horizontal asymptote, so you don't need to check for that. Let's see. X-intercepts, y-intercepts. So for x-intercepts, we would set the equation equal to 0, which really just means x squared minus 2x plus 4 would equal 0. And let's see, that is not going to factor, is it? So we have to use quadratic formula. So x equals 2 plus or minus the square root of 2 squared minus 4 times 1 times 4 all over 2 times 1, which will give us 2 plus or minus the square root of 4 minus 16, which gives me negative 12. This is imaginary, right? So since this is imaginary, can you graph something that is imaginary? You cannot. So this tells us that there are no x-intercepts. The x-intercepts that we have are imaginary, so you don't actually have any. Then we're going to plug in 0 to our equation to find the y-intercepts. So that is going to be, so we've got f of 0 would be 0 squared minus 2 times 0 plus 4 over 0, was it minus 2? Okay, so we get 4 over negative 2, which is negative 2. So we have a y-intercept at 0, negative 2. So we highlight things we know. Slant asymptote, we've got a y-intercept, we know there are no x-intercepts. Let's do continuity domain, vertical asymptote sort of stuff. So whenever we look at our domain, what would give us problems here? Denominator. So x cannot equal what? 2. And it will not cancel with the top because we've already checked for slant asymptote. So what will that look like at x equals 2? It doesn't not cancel, so it's a vertical asymptote at x equals 2. And then we have to do the derivatives and check those. So f prime of x, we have to use the quotient rule for. So we would have x minus 2 times the derivative of x squared minus 2x plus 4, so that would be 2x minus 2 minus x squared minus 2x plus 4 times the derivative of x minus 2, which is just 1, all over x minus 2 squared. So, for the sake of time, I'll tell you that's going to be x times x minus 4 over x minus 2 squared. Alright, so critical points would be x equals 0, x equals 4, and x equals 2. Although, x equals 2, what do we know about it already? It's a vertical asymptote. So that is not actually going to be a maximum or minimum at all there. So 0 and 4 are possibilities for maximum and minimum. Okay? Second derivative. It actually probably is going to be easier to do this x squared minus 4x over x minus 2 squared. I think it's easier to take the derivative if that's distributed there. So we'll have x minus 2 squared times 2x minus 4 minus x squared minus 4x times 2 x minus 2 times 1 all over x minus 2 squared squared, so that'll be to the 4th power. And again, on this one, it's probably easier to factor out the x minus 2 because it can cancel with one of the x minus 2's in the bottom. So I will do that because I think that part's tricky. So you got x minus 2 factored out. That leaves you with x minus 2 to x minus 4 for that first term. And then you'll just have minus 2 times x squared minus 4x for that second term, all over x minus 2 to the 4th power. So we must simplify more. The x minus 2 can cancel with one of these x minus 2's in the bottom. We have to FOIL this out, so we'll get 2x squared. We'll get minus 4x, so we'll get minus 8x there in the middle, plus 8, minus 2x squared plus 8x, so that's good. Some stuff cancels there. And then so this cancels, and this cancels, and we're finally left with 8 over x minus 2 to the 3rd power. And what will our critical points for the second derivative be here?
2 and 8. No.
Just 2. Okay, so if we do a sign line, I'm actually probably on this sign line. I'm not going to make a chart on this one because 8's always positive, right? I really only care about the sign of the denominator. So if I plug in a number like 0, I will get negative 2 to the 3rd in that denominator, which will give me a negative value. But if I plug in a number like 3, I will get a positive. So it's concave up here and down here. Also, I had maximum and minimum point, or possible maximum and minimum points I need to check, right? Those critical points were 0 and 4. So, it's not. Don't know what I'm thinking. It would be down, and then up. And so 0 is a critical point of my first derivative. So what am I going to have right there? relative max, because if it's concave down, that would be maximum. And then 4 is here. That's going to be a relative minimum. Only. Now we can graph. Alright. So we have a slant asymptote at y equals x. So that is this line right here. We have a vertical at y equals 2. So that is here. Okay. We had a y-intercept, where was it? 0, negative 2. I also know 0, negative 2, right there, is going to be my relative maximum, because I have a relative maximum at x equals 0. I have a minimum at 4. If I want to know exactly what point that is, I could plug 4 in to my equation. Let me see if I did that here. No, it does not. It looks like it would be 1. I think it's at 6 though. 4, 6. You would just plug it in to be able to tell. So that's your relative minimum point. And then your graph should be concave down over here. And your graph should be concave up over here. So it will look like that. And we're going to graph it on Desmos to see, but let me give you your assignment so you can be writing down and packing up. Alright, so on this one, let's do, this is page 253, and let's do wait, I'm on the wrong page. Let's do 5 and 9. 5 and 9. Yes, yes. Can I see yours, please? And I want a Desmos graph.